So different materials take different amounts of energy, heat up and cool down. They basically store thermal energy at different rates. A common one that we deal with all the time, of course, is water. And we have to, if we want to take a warm shower, we need to heat water up to a nice warm temperature. It takes a certain amount of energy to heat water up to the temperature that we want. There are other materials that we might use as insulators that may take a lot of energy and not change their temperature very much. So we're going to just illustrate this concept of the specific heat capacity of water and lead, two different materials that turn out to have very different specific heat capacity. So specific heat capacity is how much energy is required to change the temperature of a given amount of a substance by a certain number of degrees. And so we're usually measuring it in degrees C, and a change in temperature of 1 degree C is equivalent to a change in temperature of 1 Kelvin for either 1 gram or 1 kilogram of the material. So what we're going to do here is I've got a block of lead, and it's sitting on a scale here that tells me it's 356 grams. And then I've got 2 beakers. Now this beaker is marked off with an arrow at 356 milliliters because 1 milliliter of water weighs 1 gram. So I'm going to put 356 milliliters of water in this beaker, and that is equivalent to 356 grams of water. So I've got 356 grams of water in this beaker, and then I'm going to add 356 grams of lead to that beaker. So the total amount of material in this beaker is 712 grams, half water, half lead. Then I've got temperature sensors here. This one is showing it's 21 degrees C in the room. I'm going to put that temperature sensor in the water, and we measure the water is at room temperature 22 degrees C. Now I'm going to take this beaker, which is marked off at 712 milliliters, which means 712 grams. So the same total amount of material that we've got in the first beaker, except this time this is going to be 100% water. So we're going to fill this up to that marker. It works out to be just the right amount of water. So I've got the same amount of water, the same amount of matter in each material, and they're starting off at the same temperature. Here I've got another temperature sensor that's showing the temperature for the water. They're both at 22 degrees C, and I've got 2 heaters here that have been turned on to the same level, and I'm now going to put each of these on a heater at the same time. So I'm now pumping energy into these 2 containers. Each one has 712 grams of matter in them. One of them is all water, and the other is half water and half lead. And we'll see what the temperatures do for these 2 different samples over time. So I'm putting energy into them at the same rate, and I've got different amounts of, different types of stuff in there. Same amount of material, different types of material. So right now we're at 26 and 25, 26 and 26, 27 and 27, so they're both heating up, and we're just going to sit and watch how the temperature changes for these 2 things and see if they change at different rates. So we're starting to see that the combination of water and lead is heating up faster than the beaker that just has water in it. Now we've put the same amount of energy into each of these 2 beakers because these 2 heaters are turned on at the same level, so they're both putting energy into these 2 beakers at the same rate. That means the same amount of energy has been added to this beaker as has been added to this beaker, but notice that the temperature of the 2 beakers is quite different. Right now we're at 53 degrees C for the water and the lead, and we're at about 45 or 46 degrees C for the pure water. So the same amount of energy has resulted in a higher larger temperature change for this combination of materials than for this combination of materials, and that must be due to the lead. So it is easier to change the temperature of lead than it is to change the temperature of water. That tells us several things. So for example, remember that we've got, it looks like it's less stuff, but it's the same amount of mass. We measured the mass of this lead. There's 712 grams in each of these beakers. And so the difference is that it is easier to make the atoms in a block of lead move around, and temperature is a measure of how fast those individual atoms are moving around. And so by putting energy into the lead, they're responding more quickly than what's happening in water. And that has to do with the molecular structure of water compared to the atomic structure of lead. So which material do you think would be a better insulator, for example? If you wanted to put something in the walls of your house to keep your house cool in the summer or warm in the winter, would it be better to fill it with water or lead? Well, it's harder for the water to change its temperature, so the very hot temperatures outside in the summer will not cause the water to heat up as much, so you'll have a cooler water barrier in the wall that's got a higher specific heat capacity. That means it takes more energy to raise its temperature than it takes to raise the temperature of lead, which has a lower specific heat capacity. It also means that once this water, which is now at 53 C, you can see the separation is getting much larger. The water and lead combo is at 65 C. That means that if they were both at the same temperature, there would be more stored energy in the water than there is in the lead. Because to get this one up to the same temperature as this one, I'm going to have to do more work. I'm going to have to put more energy into the beaker of water. So it stores more energy in the mass of the water than you do in the lead. And that also has some practical implications for if you're wanting to heat something up and use that thermal energy overnight. So maybe you want to warm something up in the daytime in the sunlight, store that thermal energy, and then use it to warm things at night. It would be better to use water for that purpose than lead, for example. And you can see the separation is getting bigger and bigger, just illustrating the difference in heat capacities for different